All right, so if you're watching at home, you can find this printout of the notes in the same folder that you're finding this video, so you'll have seen it already. So print this out, and we'll use this to kind of walk through together. It says it's a discovery activity, which in educational language means you're supposed to be able to kind of do this on your own and discover what the rule is. There's really very few things in calculus that I can just hand you a worksheet and say, here, just, follow the steps and you'll figure it out. There's not a whole lot left that you can do that with at this level of math. In elementary school, even in algebra, we can do that kind of thing, and you can figure some things out and be like, oh, cool, there it is. It doesn't work real well with crazy derivatives. So it tries to walk us through it. It's a good worksheet, but to call it a discovery activity is maybe a little bit ambitious. So we'll do it together and maybe discover together what's going on here. Let's actually back up a second and talk about what a function is, because we're going to need a really good understanding of that to do derivative of an inverse function. So even before we get to derivatives, we're actually going to go a little bit in reverse order here. We'll talk about functions, then we'll talk about inverse functions, and then we'll worry about derivative of a function. So we're supposed to know functions really well, which we probably do. We're supposed to know inverse functions, which maybe. And so let's just back all the way up to the beginning and work forward here. So let's first look at what a function is. You might remember these kind of pictures where you have inputs and outputs. Vending machines is sometimes what we talk about. If you push one button on the vending machine and you get one drink out, that's a functioning vending machine. If you push a button and you get two drinks out, that's great for you, but that's not a functioning vending machine. That's not a function. So each button needs to go to one output. And it's okay if more than one button goes to the same output. Like think about a vending machine, especially the ones in our school, those water vending machines. Like all the buttons give you water, but it's still a functioning vending machine. If you push a button, you know what you're going to get, even if it's water every time. Okay, that's an okay vending machine. What would not be an okay vending machine, what is not a functioning vending machine, would be if you hit button 1. I mean, you would like this vending machine, but it's not a functioning vending machine. If you hit button 1 and you get a Coke and a Dr. Pepper, it's like, hey, great, it's my lucky day. But that's not a functioning vending machine. Maybe you hit the Sprite button, you get a Sprite. Good for you. That one would be functioning, but because of this messed up button that's spitting out two drinks, spitting out two answers, two outputs, that's not a function. Now, there's one more word we need to talk about when we talk about functions, and that is a one-to-one function. And a one-to-one function is where you can go backwards, where if you went backwards, it would be a function. So, like, this is not a one-to-one, because if I'm standing next to this machine holding a number 4, holding my water bottle, it's like, think about this down at the water bottle vending machines. If I'm standing there holding the water bottle, you have no idea which button I pushed because there was a bunch of options. If you can go backwards, that means it was a one-to-one function. So each button maps to exactly one output, and each output came from exactly one input. So if I'm standing next to this vending machine and I'm holding a number 4 drink, you know that I pushed the number 1 button. That's the only way it would have worked. It's a one-to-one function. If I'm standing there holding a number 5 drink, you know I pushed the number 2 button because that's the only button that outputted to number 5. So functions, not a functions, one-to-one functions. One-to-one functions can go backwards Inverses means go backwards, and so one-to-one functions have an inverse. So that's the big deal for today, is we're going to be dealing with one-to-one functions because we need the inverses we need there to be an inverse in order to have an inverse function. So this is a little bit of background music, because if it's not one-to-one, we can't do what we're going to do today. So everything we have today is going to be a one-to-one function, otherwise we couldn't do this. So we have to have a little bit of understanding, but then we can almost take it for granted because they're all going to be one-to-ones, otherwise what we're going to do today wouldn't work. All right, so functions, check. Inverse functions, maybe kind of check. Just means you can go backwards. If you're standing there holding the drink and you could tell what button I pushed, then it's an inverse function. If you're standing next to the water vending machine, you don't know what button I pushed. That's not a one-to-one function. All right. So now let's sort of walk the path toward derivative, and it'll take a little while to get there. But I really like this worksheet. I think it helps us understand what's going on. All right. Given f of x equals 2x plus 5. Graph f of x. Okay, that's a line. I can do that. Y equals mx plus b. So I'll go up to 5, and then I'll go up 2 over 1. And there's my f of x. There's the function. Is f a one-to-one function? Well, we kind of know the answer because there's only one way that this will work, and so the answer is yes. But the reason the answer is yes, or one reason the answer is yes, is that for each output there was only one input. Another way to say that is it passes the horizontal line test. Do you remember the vertical line test for functions? Yes, no? Well, if it also passes the horizontal line test, then it's a one-to-one function. Why does it matter? It matters so that the inverse is a function. Ugh, can't really read that. Matters so that the inverse is also a function, so that we can take a derivative. Point B has, or part B here, was on a test 2 tests ago, I think, where just a matter of I gave you a point and I asked you for f of 1. And most of you got it, but a few of you, I guess, panicked on your algebra. If the point 17 is on the graph, what's f of 1? Yeah, you're like, 7, I think? Yeah, that's just a different way to write that. F of 1 is 7, meaning if x is 1, y is 7. In fact, that's on the graph here. Let's make a little bit bigger point there. That's 17. I don't want to label it because we're going to put some more stuff on the graph, and things get a little bit crazy on our graph if we put too much. So just make it a little bit bigger. That's the 0.17. All right, find f prime of x. Well, if f of x is 2x plus 5, what's f prime equal to? I heard somebody say it. 2. So a little bit unrelated to this, or what we're doing today anyway, what's the slope of this line? 2. What does the derivative tell us about a function? Its slope. So here's another instance where slope and derivative are telling us the same thing. F prime is 2. Evaluate f prime at the point 17. F prime at 1. Well, the slope everywhere is 2. It doesn't matter what x is. or you just look at the picture, the slope everywhere is 2. So f prime at 1 is 2. Find f inverse and graph it. Do you remember how to find an inverse from algebra and pre-cal? You switch the x and the y. So I'll have x equals 2y plus 5. But I can't really graph x equals 2y plus 5. So I will solve that for y, and then I'll be able to graph it. So x minus 5 equals 2y. So y equals, if I divide everybody by 2, 1/2 x minus 5/2. 1/2 x minus 2.5, if that looks better for graphing purposes. And graph it. Okay, I'm gonna do a different color to graph it, but it doesn't really matter. So I'm gonna go down 2.5. And I'm going to go up 1 over 2. And this is going to feel a little bit weird because I'm not on the grid anymore because of that 2.5. But I can still go up 1 over 2. I'm just constantly off grid. So it's doable, it's just be careful. Probably redo the worksheet so it doesn't have that 2.5 thing. So there's the inverse. By the way, that switch x and y, that becomes a huge deal for this problem. So to find an inverse, you switch x and y. We'll need to remember that. All right, is f inverse a one-to-one function? Yes, because f is one-to-one. I mean, one-to-one means you can work it either way. So if one of them's one-to-one, the other one's one-to-one. You don't have to worry about it. How would you know without graphing it? Oh, I think I answered that question already. F is one-to-one. It also passes the horizontal line test. I guess that was the first test I was supposed to use. I didn't realize, wait a minute, if the original function is one-to-one, then its inverse has to be one-to-one. Part G, find the derivative of the inverse of f. Okay, well this looks bad, maybe, all the symbols there. But the inverse is 1/2 x minus 2.5. So if I want the derivative of that, so I'm looking at the other side, I'm not looking at the weird symbols anymore. What's the derivative of 1/2 x minus 2.5? 1/2. Okay, kind of store that away for a minute. What point on the inverse corresponds to the point 1,7 that lies on f? Okay, well if we switch x and y, then that point that we highlighted up here, 1,7, is now the point 7,1. Okay, those kind of traded places. Their x and their y switched. So 1,7 became 7,1. So 7,1 is the point on the inverse. 1,7 was the point on the original. Write this in function notation. Well, that means if the x is 7, the output is 1. If the input is 7, the output is 1. So 1, 7, 7, 1, they're kind of sister points for this problem. they go together. They switch the x and the y. All right, evaluate the derivative of the inverse at the point. Maybe words helps. Derivative of the inverse at 7, 1. Well, we already did that. The derivative of the inverse at 7, and really the derivative of the inverse anywhere, the slope of the inverse is always 1/2. Okay, part J is this eureka moment that you're about to have, that it's all going to click and you're going to, oh, this is so easy now. What do you notice about your answers to D and I? So what do you notice about the answers to D? D was f prime of 1 equals 2. I was f prime, the derivative of the inverse at 7 was 1/2. So what do you notice about 2 and 1/2? They're reciprocals. Reciprocals. So the derivative of the inverse at 7 is 1 over the derivative, not at 7 though, but at the sister point, the matching point, the corresponding point. Earlier Tyler said he liked dy dx as his favorite symbol for derivative. To find inverses, we switch x and y. So if we switch x and y, it would flip it over and be a reciprocal. So writing it like this and remembering that inverses are switch x and y, that might also remember that it's a reciprocal. And flip it over. Let's do another one together. Given f is x cubed plus 3x minus 5, is f a one-to-one function? Okay, you don't know why yet. I'll tell you why in a minute. It is. Although it may not be initially to look at it, because x cubed, generally speaking, looks like that. Right? And so you're thinking it might have this dip in it, which would be not one-to-one. But let me see if I can convince you that it is one-to-one. How can you tell without graphing? Well, I think these questions are asked a little bit out of order because you don't know this stuff yet. It's always increasing. And your question should be, well, how do you know it's always increasing? I can't tell by looking at that. Well, f prime, this is actually what we'll do in the next unit, a lot of this stuff. F prime would be 3x squared plus 3. And what you don't know yet really is that is always positive, right? Because if I square something, it turns positive, and then I add 3, it just gets more positive. So that's always positive. That means the slope is always positive. And that means that it's always increasing. So it's cubic, but it doesn't look like that. It looks, something like that, where it's always increasing. This stuff we don't really know yet, so you don't have to worry about it. If that was a little bit weird, you're not going to have to come up with that on your own. The point is it's one-to-one, and so we can do what we want to do with it. there's a point on F in which the y-coordinate is 9. What is the x-coordinate at this point? Okay, so if the y-coordinate is 9, that means 9 equals x cubed plus 3x minus 5. That doesn't look, I don't know how to solve that. So it's a little bit of guess and check. If I try 1, 4 minus 5, that doesn't work. If I try 2, that would give me 8 plus 6 minus 5, that would be 9. So x equals 2. So that point, if x is 2 and y is 9, so that point was 2, 9. That's not exactly what it asked, but I want to write it like that. Part C, what point on the inverse corresponds to the point you found in B? So what's the sister point? Well, if you switch x and y, that point would be 9, 2. All right, those are the corresponding points. Write this point in function notation. Well, okay. 9 is the input, 2 is the output. Now, part D is where our questions are going to, what all the questions will look like today. Find the derivative of the inverse at 9 without finding a function for the inverse. So in that first example, we were able to find a function for the inverse and take its derivative. But if I switch x and y on this, well, that's fine. That's the inverse. But I can't solve that for y. And I guess I could do implicit and do 3y squared dy dx plus 3 dy dx. I don't really want to do that. That's a lot of work. And it specifically tells me don't find that inverse function. So the derivative of the inverse at 9, I'm going to switch x and y, and I'm going to do the reciprocal thing, is 1 over the derivative of the original at 2, at the other point, at its sister point, at its matching point, at the point that goes with f, not the x that goes with the inverse. So my job is now to find the derivative of f at 2. And this is pretty easy. This is just power rule stuff. 3x squared plus 3. So f prime at 2 would be 3 times 4 is 12, plus 3 is 15. So the slope of the original function at 2 is 15. That means the slope of the inverse at 9 is 1 over 15. We switch the x and the y, we switch dy dx upside down, and we get 1/15. Can you write a rule for finding the derivative of the inverse function without actually finding the inverse? So if we want, I end up making a table for this and filling out the pieces of the table. So this is kind of the order that I'll go. So the point that I'm looking for is the derivative of the inverse at AB. But that means that these two things have to trade places. And then what I can find is f prime at b. That's usually easy to find. And then the derivative of the inverse at a is 1 over whatever that derivative at p was. So the derivative of the inverse is the reciprocal of the derivative at the sister point, at the corresponding point. Crazy enough? I feel like this is one of the hardest lessons of the year. So if you feel like, man, what is going on? It's all right. We've got another day to review and go over this. The assignment on the calendar isn't right. I want to do a worksheet, and I'll post answers. So let me pass that out, or you go print it out right now if you're at home, and we'll do one together. So here is the homework. This worksheet is located in the Schoology post folder, but omit 5 and 7. You might also notice that 1 through 6 are without calculator. 8 and 10 are with calculator. Though I omitted 7 and 9 because you need a calculator for 7 and 9. You don't really need a calculator for 8 and 10. So you can use one, but it's not really even helpful. All right, 1 and 2 I think are fairly straightforward. Let's do 3, and then we'll see if we can do 4 if we have time. I don't know if we will or not. Yes, ma'am.
Are we omitting 7 and 9 or 7 and 5?
7 and 9. Did I say 7 and 5?
Yes.
Sorry, and then I marked out 7 and 9. Omit 7 and 9. Okay, the other part about these is you've got to read the directions really carefully on these. For the problems below, find the derivative of the inverse at the specified value of x. So the x they're giving you is the x that goes with the inverse. So I'm going to kind of make that table I tried to make earlier. So the point and the derivative. But that 1/2 is, oops, that should be inverse, not derivative right there. That 1/2 is the x value for the inverse, not for the original. Which means that it's the y value for the original. So that's the first part that gets people confused, is it pretty clearly says x equals 1/2. Yes, but the directions indicate that x is for the inverse, not for the original. So put that 1/2 as the x for the inverse, and then that means it's the y for the original. So what we need to find, what we want to find, what our final answer is this, the derivative of the inverse. But I got to back up a couple steps because that's going to be the reciprocal of this derivative. But I can't find that until I know the x value for the original. So 1/2 is the y value. So if 1/2 equals sine of x, trig. So what angle has a sine of 1/2? Strained faces all around. Pi over 6. So x equals pi over 6. we need that because that's where we want to find the derivative of the original at. And once we have that, we'll flip it over to get the answer that we want. So derivative of sine is cosine. Now we want to find that derivative not at 1/2, because 1/2 is the x value that goes with the inverse. We want to find it at pi over 6, because that's the x value that goes with the original. Cosine of pi over 6. Well, this shouldn't be too hard. We just realized the sine of pi over 6 is 1/2. So the cosine has got to be that other value, root 3 over 2. And so root 3 over 2 is the derivative of the original at pi over 6. The derivative of the inverse at 1/2. How am I going to get that? If I know this answer, what goes in the box? How are they related? 1 over that. I'm just going to flip it over because inverses and originals are reciprocals, or you switch the x and the y, which for dy dx means you get a reciprocal. So my answer is 2 over root 3. So my encouragement to you is to set up that little table thing. Let's start number 4, and we'll have to abandon ship after a little bit. But I think the table thing is helpful. F inverse with a point and a slope. And the answer we're always going for is the derivative of the inverse, but we just got to wind our way there. So the first thing they give us is x equals 1, but that x equals 1 is for the inverse. Which means that our y value for the original is 1. We're kind of backing our way around to land at that box. So 1 equals cosine of 2x. This is kind of a pain. So 2x then has to be, what angle has a cosine of 1? What's the angle that has a cosine of 1? Forget the 2x part. What angle has a cosine of 1? 0. So that means 2x has to be 0. So x equals 0. Okay, so that's not too bad. So now I need to find the derivative evaluated at 0. That'll give me this spot, and then I'll flip it over to get my answer. So f prime is, oops, this is the other way. Derivative of cosine is negative sine of 2x, and then times 2, chain rule. At 0, hey, we're going to get through with this one, I think. Negative 2 sine of 0. What's the sine of 0? Right, there's the angle 0. So that's 0. And here's why I wanted to do this one. So the derivative of the function at 0 is 0. So the derivative of the inverse at 1, what happens when I flip 0? Undefined. So you could write 1 over 0. Don't leave that as your final answer because that's not really okay. But undefined. And remember, that doesn't mean we don't have an answer there. That just means the slope would be undefined. You'd have a vertical tangent line. All right, you're packing up, but the answer to number 1 is 1/5. The answer to number 2 is 1/13. The answer to number 5 is 1/13. Answer number 6 is 4. Number 8 is 9, and number 10 is 1/2. Give those a try. We're not doing anything new tomorrow, so we'll go over a bunch of these. We'll have some review questions, and then you'll have Wednesday completely on your own to review, and then Thursday we'll test.